So today we are going to see the project on estimation of power and delay of CMOS phase detector and phase frequency detector using, that is, MOS transistors. Okay, so what is the first of all what we are doing here? We are working on the power and delay. Okay, so first thing, why we are going for the VLSI circuits, in the sense, the mainly three reasons. First thing is power. Okay, then next speed, or you can say delay also, delay, and next, that is area. Okay, so day by day the requirements are increasing, that's why we need more speed. Is it? We need more speed. Then power, what about the power? As we know, the requirements are increasing day by day, so we want our power consumption reduce should reduce day by day, so that we can use our gadgets so for the long time, or long battery life. Okay, so this is the purpose why we are going for the power, and then next, why we are going for the speed of that circuit. Then next, as the complexity is increasing, so there might be chances of increasing the chip size. So if chip size will increase, so means the device can't be a portable. To make device portable, so we are focusing also on the areas. Got it? So these are the three major factors why we work on the VLSI technology. Without this, there is no any project. Okay, so you can't see any project depending upon, means like out of this power, speed, and area. Okay, so here we are working on the same thing. So we are working on the power, we are working on the delay. So that too, we are working for the CMOS phase detector. So what is a phase detector? So what is a phase detector? So
Which
can you know
detects
it?
the difference. Which
Yeah,
detects the difference in phase between two signals.
yeah, it detects the phase difference between two signals. So what is the first signal? Suppose, see here. So phase detector is the first block of phasor lock loop. You know. So you might know that. So in phasor lock loop, you can see this is the first block, that is phase detector. Then next, we are having low pass filter. Then next, VCO, voltage control oscillators. And then next, here I am having some output. So that output is given as a feedback to the phase detector. And this is the input signal for the phase detector. Okay. So as we know, we are working on the digital circuits. So that's why in digital, there are two types of phase detectors. So those are XOR, means by using XOR, and next is phase frequency detector by using D flip-flop. D flip-flop. So already we are having XOR and D flip-flop. Then what is the need to work on this? Okay, suppose the previous XOR gate is having power consumption . So power consumption, like suppose 10 microwatts. I'm considering this as a 10 microwatts. But Now what we have to do, we have to find the minimum power. So that is what the extension called. So we have to get some minimum power from this. So now whatever we do extension for that, so it should be like 8 microwatts or less than that. Okay. And the delay should be, so it should be reduced with the as compared to the extension that is existing one. So like that for D flip-flop also, that is phase frequency detector. Okay. So why need of these things? See, suppose a circuit is there. So this is all nothing but phased lock loop. Okay. So if I am giving the inputs and if I got the output after 1 hour, so what is the use of that? No use. As we are moving, like where our requirements are and our expectations are reaching high. So what we need less power consumption then also. And what we have to do, so that is less delay, that is nothing but speed. So we need our output in the fraction of seconds. Okay, so this type of this phasor lock loop works in the demodulations of signals. So you know demodulation, this is in the communication topic. Demodulation. Demodulation. So suppose this is my carrier signal and this is my message signal. So it sees the difference between this phase detector, it sees the difference between the message and carrier signal. So if message signal and carrier signal will match and its difference is 0, then it is called in locked condition. Okay. If difference is, suppose message signal minus that is carrier signal. So then if it is 0 difference, so then it is in locked condition. Otherwise that is not. Okay. Otherwise there is a error in our signals. Okay. So this is the thing, guys. So here in this paper, now some circuit has been given here. Just see. So what is that circuits? Okay. So that is phase detector. Just see. So here in figure 1, it is given like CMOS based phase detection circuit. So by the help of, which is designed by the help of XOR gate. Okay. So why XOR gate? So you see, if you know the truth table of XOR gate, it is like this. A, B, so 0, 0, 0, 1, 1, 0, and 1, 1. So if these two signals are same, then the XOR gate output is 0. If the signals are different, so nothing but the difference is 1 here. So that is why mostly we use XOR gate. Okay. So that is the thing here in our base paper, we are using XOR gate. You can see this is the XOR gate. So do you know how to design this CMOS XOR gate? So if you are having any idea, so I won't go for it. If you are having idea, then I will. So if you don't have any idea, then I will go for it. Just tell me. And one thing, my voice is visible to you or not?
Yes, sir, your voice is clear. Like
Okay.
I have simulated these gates in LT Spice, but in Tanner tool we don't have an idea. So if you would help in that, it would be of good
Yeah.
thing.
Okay. Yeah. Okay. So you know how to make this design, is it?
Yes, sir.
Okay. So then not an issue. So here I am having a Tanner software. This is my Tanner software. So I will show you from the beginning. Just I'm closing that. Then see, this is the S-Edit. So this is the Tanner software Spice Edit application. So here we have to open that application. Then next, what we have to do? So we have to take a new. So do you have Tanner with you? I think you don't.
Yes, sir.
You
I
are
have
having.
Tanner tool. Yes, sir.
So which version is there? 16?
Yes, sir.
Okay. So you can see here we are having like menu options like file, edit, view, draw, cell, setup, all those things. So what I am having, so I am having a file. In that file I am having a new. So new design. So we are going to design something new. Suppose I am taking like training class, something, whatever it may be, you can take. Already your Cmos face detector is done, designing is done. So I am taking like this. Okay. Then next you just click OK. Then next we have to add the libraries. So there are some libraries given in this. So we have to add that. So you can see here. So all these are libraries. So we have to add one by one. Suppose I'm adding this one. So just so here I got like all those libraries. Now next thing we have to design we have to design the circuit. For that we need a cell. Okay, so we have to create a new cell. So suppose I am giving like inverter, okay, INV. Then next click OK. So you will get a like black screen. Then next for inverter what we need, so one PMOS and one NMOS. So this is the PMOS I am taking. So this is my PMOS, done. And this is my NMOS. And this is the NMOS. So now, as you know, inverter, so both the inputs are sorted to some input A or whatever it may be. So here I will get the output. And now, so at the source of PMOS, VDD is given. So in this MISC, okay, we are having options like ground, VDD, all those things. So we have to take VDD. Then next, ground. So we have to take a ground. So then next, I have to give the inputs. So here are input port and output ports. So here you can go for the inputs. That is IL. Then next, output. So we have to take the output from here. That is done. Now, so if you run this, you won't get anything because you have to take the inputs now. So what is the input? See, that is taken by the help of voltage source. So you can see here voltage source. So first thing we have given here VDD, is it? So now for that VDD we need some voltage. So take voltage source, then here DC of 9 is given. So just take it. Then next, so plus is connected to the supply. So I am copying it and then next just I am pasting over. Then next ground negative. So that is here you just see plus and minus is given. Okay. So minus is connected to the ground. Then next again I am having one input. Now for that also I have to take a voltage source. So go to spice elements in voltage source. So you can see the bit of 9. So there you can take the input values. So this is the input and negative pin is connected to the ground. Now if you click this, here you will see the pattern. So what is the pattern? 0 1 0 0 is given. So I want to change it like 1 0 1 0 1 0 like that. So now I want to show this output, okay, show this circuit output into a graph. So then what I have to do? I have to print that output. So for that, I am having options like spice commands. So here you can see. So next in that spice commands, you are having print voltage. In that print voltage, so we are having options such like this is the print voltage. If you can see this, so this is the print voltage. So first print voltage, I am giving it to the input. So I am giving it to the input. Second print voltage, I am giving it to the output. Now next thing, here you can see setup simulation. So in this setup simulation, we have to go for the transient Fourier analysis. In this transient Fourier analysis, you can take your stop time. Suppose I am taking 40 n. Okay, so and maximum time setup, that is 1 nanosecond I am taking. So next, in this same setup simulation, you have to call your library files. So here you can see the library files. Then next, from here you can call the, that is generic tech. In that generic tech, you can see generic 250 nanometer lib. From that, you can call your library files. Then after that, what you have to do, once you selected with the library, give space and then TT, okay, capital log TT. So then you just have to run it. So now you will get the output. So let us see. So it is loading. So it takes like some 1 minute of time. That's it. Okay. So now you can see this is the graph. So you can separate these plots. Then my input is 1, output is 0. And again, input is 1, output is 0. Input 1, 0. So I am getting a perfect inverter. So now for this circuit, inverter circuit, I want to find how much power it is consuming. So let us find. So for that consuming power, so we have to go for the T spice. So just double click on that, you will get it. So here it is open, whatever I have created a file. So you just see this file cell name is INV. Okay, so it is created in the T spice. Now in this, what are the voltage source I have taken? For input itself we have to consider. So for input I have considered like VT2 VV2. Okay, then simple command, that is dot power PV2. That's it. Save and run it. So no need to see the graphs. So now you just see here, average power consumed by this circuit is 2.27 exponential of 007 watts. So what is that? 2.27 exponential of 007 watts. So how can I convert these things? So just see, this is like 2.27 into 10 to the power of minus 0.07. Okay, so I want to make it into microwatts. So for that purpose, you can do it like this: 0.22 into 10 to the power of minus 6. which is nothing but 0.22 microwatts is my microwatts is the power consumed by the inverter circuit. So this is the thing how we have to check the power. Okay, next. So like that, in this, whatever the circuit has been given here, so first circuit is given like XOR gate. So now just find we will find the XOR gate power consumption and its output. So let us see. So already I have designed here. So like phase detector circuits has been designed. So this is my Cmos phase detector. So just click that. So whatever the circuit diagram is there, so I have designed according to that. The next, see here inputs, I am having A and B. So A, I have taken like something 101010 something, and B, I have taken like 1010. This is also I have taken same thing because it shows the difference, is it? So now just go for the simulation. So let us see. So it is showing the phase difference at this point, means you can see output, that is output V. This is the phase difference, and this is the phase difference, and this is the phase difference. So we can make this amplitude, whatever the gap is there, we can make it short, not an issue. Okay, so this is the phase difference through by using XOR gate. So next thing, again, if I want to check the power consumption for this, so what I have to do? So I have to go for the T-spice. Then next same. So how many input voltage sources are there? So that is VV1, VV2. These two input voltage sources are there. So that's why dot power. So VV, sorry, caps lock we have to take VV1 and dot power VV2. And for dot power, you can take caps lock or small letters. It doesn't matter. But for this voltage VV1, VV2 voltage source, you have to take caps lock itself. Okay, means in capital letters. So now just run it. So what I got is the power consumption consumed by this circuit is 1.0 into 10 to the power of -6, nothing but 1.01 microwatts and 1.64 microwatts. So now this is the VV1 for VV1, average power consumed by the VV1, average power consumed by the VV2. Now what we have to do to get overall, so add 1.01 and add 1.64. So whatever the value we get, so divided by 2. So that is the average power consumed by that circuit, overall circuit. So this is the power consumption. Got it? So nextly, what we have to do, so there is another circuit given in our paper. So that is, so phase frequency detector. Now phase frequency detector is given with the D flip-flop. So what I have done, so I tried to reduce the power consumption of this circuit. So one thing, whatever given here, I have designed in this ECET. So that is phase frequency detector. So this is the phase frequency detector, whatever given in the circuit. So what I have done, so just by running it, you can get the outputs over there. So see, so what is the, yeah. here this is like a difference in between clock 1 and clock 2. This is the difference. Okay, so now we can make like here given like 3 to 4 figures are there. So this is for the figure 1, that is figure 3. Then if I want to do for the frequency detection, clock 1 frequency is higher than clock 2. So if you just see this thing, so what is that? Clock 1 frequency is higher than clock 2. So clock 1, you can see the cycles are more, and clock 2 the cycles are less. So let us see how we can do that. So here you can see I have taken from 0 nanoseconds to 40 nanoseconds. Got it? So in between there are like it is having like 10 nanoseconds, 20 to 25, 30, 35 like that. So depending upon that, I have to decide now what I have to do. That is clock 1 I have to make it high. So how can I make high? Just see, let us do, how can we do that? So go for the clock 1. So here it is clock 1. So in this clock 1, if you see, so there is 5 nanoseconds for high transmission 6 nanoseconds, and low transmission 5 nanoseconds is given. So what I will do here, I will take like 2 nanoseconds and 2 nanoseconds. So let us see what we will get as a clock 1. So see here the difference, how it is clock 1 here, and now what I will do, so this is the previous one, got it? So what I will do, I will show you what I have done change. So I have done change for 2 nanosecond and 2 nanosecond. So let us see. So check, see here. Now you can see this box that is red color. We are getting waveforms in red color. So that is you can see that clock 1 is now high frequency. Okay, and clock 2 is means nothing but low frequency. So we are getting like phase detectors. You can see whatever we are getting. So this is the phase detector. Phase detector is nothing but it sees the, means it checks the difference between two signals. So then next, what I am doing, I want to check the power consumption, because power consumption is very necessary. Without power consumption, so see, if my power consumption is high, then suppose I have done one circuit, that is phase detector. So see, I have done a phase detector, so which is with high power consumption. So, and this phase detector, I am using this in phased lock loop. So phased lock loop, I am using this phase detector. Now this phased lock loop using in the communication system. Okay. So now that communication system, I am using it into the processor. So if one of the circuits, so if any one of the module in the processor consumes high power, okay, almost it is nothing but getting load on the processor itself. So for that purpose, so what we focus each and every module should consume less power, so that the overall power consumption of microprocessor will get less. So once the microprocessor power consumption will get like less, so battery will be the long life, means like the battery life of that whatever the device, whatever the gadget so is there, so that is like for the more time. So that is what we are working on. So here what I will do, I am trying to change this by using a technique known as CMOS dynamic technique. So what is that CMOS dynamic technique? So here you can see CMOS dynamic technique, nothing but it is called dynamic CMOS logic. So dynamic CMOS logic. Dynamic CMOS logic or CMOS dynamic logic. So here we are having like pull up network and pull down network, you know, all those things. So suppose here two transistor, in the sense we are here also we have to use two transistors, but in this dynamic CMOS, so half of the transistor will be reduced. Like how? Okay, in the sense so in this dynamic CMOS we are having two types. So either dynamic CMOS with working only with the PMOS transistors, and another is working only with the NMOS transistor, nothing but pull up network, pull down network, NMOS. So as we know, the NMOS are faster than PMOS. So next thing, suppose you can see here, so it is like this dynamic CMOS logic, it is like this. So this is my pull down network. So I will write it PDN, and then next NMOS. So this is given to a control signal. So I can use that control signal as clock. You can say whatever it may be. So I will just consider it as a clock, or you can give like CTR also, not an issue. Okay. So now this is VDD and this is the ground. Now one thing, what is D flip-flop made up of? So what I am doing, I am trying to make the power reduction for this circuit. So the major what is given here, the major thing is flip-flop given in this. So now flip-flop is designed by the help of NAND gate or otherwise NOR gate. So what I want to do, if I change the, if I make some extension for the that is NAND gate, so automatically the power consumption of D flip-flop will get reduced. Okay, because in one D flip-flop we use 4 NAND gates. Got it? Is it? So like that, one, so see, one of the NAND gate power consumption is reduced, then we are using the same thing, same NAND gates for overall D flip-flops. So that is the thing we are doing here. Now what I am doing here, so I am designing a NAND gate by the help of dynamic CMOS. So let us see how we can do that. So it is simple. Just I am having like one thing, that is a PMOS. Then next, one second. So so this is the PMOS and this is the NMOS for control signals. Okay, so considering this is the NMOS, which is must and should needed for the dynamic CMOS. So then next, in this part, so in this part we have to take our circuit. So for NAND gate, my NMOS transistor are in series. So NMOS transistor, that is A, B NMOS transistors that are in series. So now this is A, consider this is A, and consider this is my B. So which are in series. Now here this is VDD. Okay, and from here I will get the output. This is the output. Got it. And you can see this is one of the signal. You can say control signal or clock signal, whatever it may be. So suppose my control signal is 0. Suppose my control signal is 0. So 0 in the sense this is 0 and AB is also 0 comma 0. So these two are off. Okay, these two are off and control signal is 0. Means PMOS is on and this NMOS is off. Means we can see VDD is flowing through the output. Got it? So it means output is 1. So next, same control signal is 0 and this is 0, this is 1. This is 0 and this is 1. Now just tell me, so which one is on? So like B is off, A is on, and this last transistor, this is also off. Means there is no ground supply. So nothing but VDD supply is there. So again it is like 1. So then next, again B is 1, A is 0. So B is 1 in the sense this is on, this is off, and this is also off. Okay. So now again VDD supply is there. So next, suppose my control is 1 now. Control is 1, A is 1, B is 1. So all the NMOS transistor will get on. Will all the NMOS transistor get on? The ground supply will go through the output. Okay. So now we will get the output, that is 0. 1, 1, 0, which is nothing but the NAND logic. So we are getting the NAND logic by the help of Cmos. So the same NAND logic we are going to implement, means implement, and we are just checking it the power. So one thing is that we got a less power consumption if we use this CMOS dynamic. Then by the help of this, what we are going to do, we are going to design the D flip-flop. So that is what we have done here. So that is called new phase frequency I have taken, like extension. So this is the NAND flip-flop and this is the this is the the D flip-flop that is done with the new NAND gate. Okay, and this is another D flip-flop. So now what I'm taking the same inputs, clock 1, clock 2, and same whatever the we have taken for the inputs will be same as per the extension or as per the existing one. So next I'm checking it. Okay, yeah, we will get the output also similar, but the thing is that what we will get the power is the thing we have to see. So let us see what we will do with this. So just wait 1 second. So this thing, first of all, what is the previous one? So my previous one is phase frequency detector. So phase frequency detector, take it, and now open TSpice. Now in this TSpice, check the power consumption for this circuit. So dot power VV1. So input, where we have given inputs, clock 1 is given at the VV1 and clock 2 is given at the VV2. So VV1 dot power VV2. So save it and run. So this is the thing, we got the output. And next, now just see, in the TSpice output itself you will get the power consumption. So for VV1 the average power consumed is 1.16 into 10 to the power of -5, and the next one is 1.35 into 10 to the power of -7. So just what I will do, I will write it here. Phase frequency, that is existing. So two inputs are there, so voltage source V1, so average power consumed is, so I will just copy it, these two. So average power consumed by VV1, and next average power consumed by VV2. No need of these things. So now what I have to do, I have to convert this into microwatts. So 1.16 to means it is given in the 10 to the power of -5. So then we have to take like 1.6 into 10 to the power of, that is nothing but microwatts. Then next, what about this 1.35 10 to the power of 7? So I will write like 0. Yeah, 0.135 so microwatts. So this is the thing. So this is for the existing. Now let us see for the proposed one. Let us see. So previously whatever there, so I will just close it off. Now what I am doing, I am just checking it for the new phase frequency. So you can see, you can just click here Cmos phase detector, my project name, and then you can see here new phase frequency. So new phase frequency, this is the new phase frequency, and you just open it in TSpice. So now, so you have to check the whatever the voltage source is given. So VV1, VV2. So now you can go for the power command, dot power VV1 and dot power VV2. Now you can see that is 8.450. Just I will copy it first of all. So So 8.45 into 10 to the power of 7. So that is converted into microwatts. So which becomes like 0.84 into 10 to the power of into 10 to the power of 10 to the power of 6, nothing but 10 to the power of minus 6, that is nothing but microwatts kada. So I will write like microwatts. Then next, so 1.6 into 10 to the power of minus 6, so this is already in microwatts, so then I will just write it like 1.63, okay, microwatts. So now calculate these things. So 11.6 and add with 0.135. So what I will get there? So that is 11.735 something I will get. So what I am doing, I am making like a average of that. So 11 point, sorry. So 11 point, that is 735 divided by 2. So what is the output I am getting? That is 5.86 microwatts. So here average power consumed by overall circuit. Power consumed by overall circuit. Okay, so that is 5.86 something. Yeah, 5.86 microwatts. 5.86 microwatts. Then next, what about this? That is 0.84 and 1.63. So which is nothing but 2.47 if you add those things. So 2.47 2.47 divided by 2. So that is 1.235. So my average overall circuit is average power consumed by, that is new phase frequency, that is what is that, 1.235 microwatts. So now you can see, so this is the this is having high power consumption, and whatever we have designed the new one, so that is having low power consumption. Now you see this phase frequency, we are giving our input voltage, that is VDD, that is 5 voltage. Here and here we have compared by giving 5 voltage. Now you can compare these circuits by giving some different voltages like 3 volts, and here also 3 volts, and like 2 voltage or 1 volt, whatever it may be. Okay, as per our requirements. So we can change our supply and we can see the power consumption. So whatever it may be 5 volts, 3 volts, 2 volts, but the power consumption for the new phase frequency will be reduced. Now where we have to change these voltages. So here you can see, you can change your voltage at this point, that is 5.0 volt. So you can change here 5.0, we can make it into like something you want, 3.0, whatever it may be. Okay, so you can make the change. So otherwise you can make your changes over here. So 1 minute. So you can see here it is given like DC 5. Okay, so here you can make like 3 also, not an issue. So nothing but 3 voltage is supply. Okay, so like that you can make changes in T-Spice or otherwise ECET. So you can so you can make a graph whenever at 5 voltage how much power is consuming, whenever at 3 voltage how much power is consuming. So you can do that thing. So means the analyzation. by giving different inputs. So this is the thing why we are going for the power consumptions, less power consumption. So do you have any doubts in this concept?
So you are making changes only for this frequency circuit.
Yeah, frequency circuit.
And the previous circuit you have shown phase detector, there are no changes in that circuit.
Which one?
Uh, Phase detector circuit, there is no
XOR.
change. First circuit, XOR circuit.
Yeah, we can do it by the help of same CMOS dynamic logic. I will give it, not to worry. So
Okay.
just so like how uh, here you can see. So one thing. So see, this is the CMOS XOR color, XOR design. Okay. So here,
Yes, sir.
if you make this into CMOS dynamic, so this will be eliminated. This part is eliminated. Now at this part only one PMOS is taken. So only one PMOS. So otherwise I will take some different color so that you can understand very easily. So
No problem, sir. It's okay.
no problem.
Understandable.
Yeah. Okay then. Not an issue. So here what I will do, here we will take only one PMOS. So next, here what we will do, we will take it off ground and another NMOS we will give here. So now which is given to the control or clock signal. Okay. So from that you can see now. So before it was like one transistor, two transistor, four total, 1 2 3 4 4 transistors are there. You just see. Okay. So 4 transistor for pull up and 4 transistor for pull down network. Now in CMOS dynamic, so you can see like 8 transistors converted to 6 transistors, means slowly the area is also decreasing over here. Okay, got it? Just see.
Yes, sir. Yes, sir. So,
Okay. One transistor, this is one transistor and these are 4 transistor, 5 and this is 6. So if we are having like huge circuit, so if we are designing with the CMOS, then also the transistor will get decreased. So this is one of the advantage that counts of transistor also getting decreased over here. Okay, yeah, tell me.
okay, sir. Okay. And also we have implemented this in 250 nanometer technology. What you have shown now just implemented
Yeah,
in
250. Yeah,
Cmos, sir.
250.
Like by the end, in which technology, channel length, what you will be using, sir? 45 nanometer.
Yeah, one thing is that, so
Mm.
whatever we are using means whatever the software we are using, those software are open source. So we can't get like nanometers like 45 nanometer, 65 nanometer. So that we have to buy it. So that is one of the means like we have to get the license from that. So all those things will be like, so for our studying purpose and for our like for project purpose, this is enough. But presently if you see, the technology is going for the 5 nanometer. Okay, so
Yes, sir. Yes.
previous it was like 7 nanometer. In that 7 nanometer, Redmi Note 7 Pro, so whatever the Redmi Note 7 Pro processor has been launched, that was in the 7 nanometer technology. Okay, because due to the fastness, even it is designed with the 7 nanometers, so even that is having some disadvantages like hanging or some problems. Okay, because whenever the load is getting on the processor, like so many pics are there, so many data is there, storage is there, so all those things, so many applications are we are using, then almost whatever it may be, so it will get hang. So that is one of the problem. Then we are going for the 5 nanometer, then we are going for the 3 nanometer, like that. So we are working day by day. So there is no stop, you can say. Got it?
Yes, sir. Got it.
Okay.
By using predictive technology model, we can incorporate in the open source software, no, sir. Like whatever the
Yeah.
technologies they have
Ah.
implemented by using
Hmm.
PTM, we can implement, no, sir.
Yes, yes.
Yeah. So we can by using that we can do it this project in 45 nanometers too, also, no, sir.
Yes, 45 nanometers also. And
Yeah,
do
yeah.
you have this software, Tanner 16?
Yes, sir. I have this software.
Do you know the installation procedure?
Yes, sir, I have installed it and completely I have done a small circuits in that.
Okay,
Actually, like I have much experience in Xilinx domain, like in that.
okay,
So I don't know much about this Tanner technology. So for basics learning, I just asked you to show a simulation of a basic circuit.
okay, okay, okay.
So
So it's
clear
okay, not an
understand.
issue. So understand?
Yes.
Okay, okay.
Yeah.
So you are whatever the documentation will be sent to you on your mail ID. So
Okay, sir.
by today evening or tomorrow, I will let you know. Okay.
Oh,
So and
uh, by the
if you are
end of
having
this,
yeah,
yes.
if you are having any doubt, please free to ask like doubts Shiva sir. Okay.
Okay,
Uh,
sir.
so to whom you have approached, that is Ekalavya Technologies kada.
Yes, sir. Ekalavya Technologies.
So you can ask them. So that will be forwarded to me. Don't worry about that. Okay.
Okay, sir. Okay.
So so means
So
like
could you simulate
uh,
this using 45 nanometer technology, sir? PTM,
uh, what,
uh,
hello.
instead of 250 nanometer technology, we'll go with 45 nanometers technology, sir.
Okay.
Is that possible? Like, we'll simulate in 45 nanometer technology.
No, because of why? In the sense we, so whenever we download such software, some libraries we will get like 250 nanometers. So
Okay, sir.
that are the libraries given by the open source. So
Mm-hmm.
as you know, the Tanner is a mentor graphics tool. They won't release very easily these type of
Yes.
licenses. So that's
Yeah.
why we have to buy it like in bulk, like by giving them like 2 lakhs, 3 lakhs rupees, like that. Okay.
Yeah, I got your point, sir. But using predictive technology model, we can incorporate those, no, sir.
So if you are having libraries, then we can incorporate that.
Yeah. Okay, sir.
Got it?
Okay. Yes, sir.
That is
Yes.
the thing. So
Yeah.
if you are having libraries, then you can take it, not an issue. We can design it. No any problem is there. Got
Yeah,
it?
yes. Using like I want to design using that technology, sir, 45 nanometer technology. So
Okay, okay.
for paper
Even
publishing also it will be very
ah,
easy, no, sir.
okay, okay.
Yeah.
Even in the LT Spice also, we don't have any 45 nanometer right now.
Yes, sir. In
Okay.
LT
It is,
Spice we don't have it.
yeah, we
Yes,
don't
yes.
have it. So
Yeah.
whatever is there with open source, we have to manage that thing. Okay.
Okay. Okay, sir. Sure, sir.
Okay. Is it
Also,
clear now?
nothing
Yeah.
is mentioned about delay in this, no, sir.
Yeah. I will let you know the delay. So
Yeah.
here, how we have to take, oh, sorry for that. So how we
Yeah.
have to see the delay here? See, suppose this is my like 1 minute. I'll show you. This is my circuit. So let us see some easy circuit. Just CMOS phase detector is there. Suppose. So
Okay.
first one. Okay. So here you can see. Uh, so when we can see the propagation delay, that is when we give the input. I have given the input and getting some delay at the output. So that is nothing but the propagation delay. Kada. So if you see, suppose here for this, you can see for this, suppose if I am considering the propagation delay for the B input and the output. So you see it is going from 0 to 1 to 0. 1 to 0. So from this 15, okay, you can take this 15 from this 15 to here. Okay, so what is the delay we are getting? So that is so that is one of the delay in my circuit. Okay, so if you consider this point, so these at this point, so you just consider these two. Okay, and if you are now there won't be any delay by the help of means by taking B waveform into consideration. Now by the help of A consideration, so here you can see we are having these two. Okay, and next for this we are having these two delays. Okay, now what you have to do, all these delays you have to calculate. So 10 to, suppose this is like uh, it is like 10 to 15 kada. Okay, so 10, 1 minute. Suppose if I consider this is 10 and this is 15, so that means it is 12.5. Is it? So now it is around like 12.5. If you make this half, then it is like around 11 point something. Okay, so this is the thing we have to take, means we won't get any accurate, but we have to consider from here itself. So then next, from this point take the delay, and from this point take the delay, and from this point take the delay. Now from this all four you have to take the average delay of your overall circuit. Got it? For everything you have to do the same thing. Okay, means same procedure. Got it?
Yes, sir. Means you're saying that we should only calculate. There is nothing any inbuilt
Yeah, no, no, not
that
like that.
can be calculated
Yeah,
in the software.
yeah, we don't have
Yeah.
anything like that. Okay. In
Okay.
LT Spice also we have to see our delay with the help of this itself, waveforms itself.
Ah, yes, yes. Yeah.
Okay.
Got it, sir.
Okay.
Okay. All the
Okay.
material will be provided by tomorrow, no, sir?
Yeah. Okay.
Uh, and also, will there be another final explanation, sir?
So if you want, I will give it. No, not an issue. Whenever you are having like project report or project submission. So if you are
Mm,
having any doubts, so I will clear you. Not an issue. Okay. Feel free.
okay.
But
Okay.
tomorrow and day after tomorrow, there won't be anything because I am having some different works. Okay.
Okay, sir. Okay.
Oh,
Sure, sir.
okay. Okay.
Thank you, sir.
Thank you.